We will discuss a few problems on conditional expectations and stochastic process. So the first problem is, suppose x and y are random variables with some joint distribution. Suppose we make an observation y. What is the optimal estimator of x given y? We need to show that e of x given y is the optimal estimator in mean square sense. So let x hat of y is the optimal estimator of x given y, and we can split this as a conditional expectation. Ey ex given y, x minus x hat of y square. We can expand ey as ey ex and this square, and then subtract this e of x given y, and just consider the inner expectations. We have this uh, expansion, the first a square plus b square plus 2 times ab, and of course this is everything is conditioned on y, and we can take expectations as expectation is linear, and this is equal to the first two terms, and the last term is 0 as shown here. um, because this e of x given y minus x hat of y conditioned on y is a constant, we can push it back, and we can take the expectation only on this the first term, which is nothing but e of x given y minus e of x given y, and that is 0. So now this is the sum of two things and two non-negative quantities, and x hat of y is only present in the second, so that can be minimized by taking x hat of y as e of x given y. Uh, Coming to the second question, suppose we want a linear estimate of y given x. So what is the optimal estimator in this sense? So here we have to minimize e of y minus, because we are estimating y from x, right? So we just have to minimize this thing, and y hat is ax plus b, and this is, just write it as a square plus b square again, minus 2ab. It should be plus here, so that is taken care in the second step. And we need to differentiate with respect to a and b and set to 0. So we can differentiate with respect to b, and when we set it to 0, we get b as this highlighted as 1, e of y minus a times e of x, and substitute back this b into the original equation, and then again expand and then differentiate with respect to a and set it to 0. So we get finally a as e of x tilde y tilde conditioned on e of x tilde square. By the way, x tilde is x minus x bar, x e of x, and y tilde is y minus e of x, y minus e of y. And the third question is, we want to find the expected number of tosses to get k consecutive heads if the probability of getting head is b. So you can assume that mk is the number of tosses to get k heads consecutively. Mk is a random variable. What we need to find is e of mk. So one reasonable variable to condition on is the um, number of tosses required to get k minus 1 heads, right? So just conditioning on this, if we get head, we are done, because n plus 1 tosses we got it, and if we don't get head, we already had n tosses plus 1 toss, and we start all over again. And by using the law of alternate expectations, e of mk is condition e of mk given mk minus 1, and that we expand it here, and e of mk is e of mk minus 1 plus 1 times p1 minus p times mk minus 1 plus e of mk, and let nk is equal to e of mk. Nk is p times e of p times nk minus 1 plus p1 minus p nk minus 1 plus 1 minus p plus minus p times nk. And simplifying this, we end up getting a recursive equation, p times nk as nk minus 1 plus 1, and nk is 1 over p times nk minus 1 plus 1 by p. Okay, so we can back substitute this recurrence relation and we end up getting this thing. Here m1 is a geometric random variable, so that is 1 over p. And this is a question on joint distribution. So f of xy is equal to e power minus y, 0 less than x less than y less than infinity, and find the marginals of x and y. So x and fx of x is integrating over y, the type of dx here. And y goes from x to infinity, and we got e power minus x for x positive. Similarly, f of y is minus infinity fx of x comma y dx, right? So integrating x, that is going from 0 to y, we get y e power minus y greater than 0. Find the mean and variance of x and y. Since we know that this is gamma distribution and this is an exponential distribution, so mean and variance is straightforward. That is 1 and 1 and 2 and 2. Find the covariance of x and y. So covariance is e of xy minus e of x e of y. E of xy is simply integrating this over the joint distribution, and that we get to be 3. And e of xy is e of xy, covariance of xy is e of x minus e of x into e of y, that is 1. So final question is gambler solving problem. So assume a gambler starts with an initial fortune of I units, and at each successive game he wins either 1 unit or loses 1 unit with the probability p and 1 minus p respectively. What is the probability that gambler will win? So gambler wins if he attains a sum of n without getting ruined. So probability of n, as we can condition on the first toss, right? So win in the first toss and probability of winning given win in the first toss, again lose in the first toss, probability of losing in the first toss. So now this is pi is when the gambler probability of winning, the gambler winning when he has an initial amount of I. If he wins, his amount is increased to I plus 1. If he loses, the probability q, his amount is decreases to I minus 1. And p0 of 0 is 0 because he cannot win if his amount is becoming 0, and if amount becomes n, it will be 1, he wins. So just rewriting this recurrence relation like this, we can simplify to get pi to be like this, and because we know the boundary condition pn is 1, and can substitute I to be n minus 1 here and obtain p1. So finally we get pi to be 1 minus q by p whole power I, 1 minus q by p whole power n. If p not equal to q, and if p is equal to q, it is I by n, and 1 minus pi is a probability of ruin.